Yes, sir.
Okay, so I got to get me back here. And yeah. Okay, so I think we're okay. Anybody else comes and anybody knows that, you might tell me. But I will put that up. We will have 14. We have everybody. Okay, so I don't need to worry about that. All right, so with polar coordinates, one of the things I hope you've done is looked at the book and looked into some problems and stuff to find out how to convert back and forth. That's the first thing. Also, by the way, before I go too far, we do have a test that's coming today, you all know, and that's due a week from today at midnight. Hope everybody knows about that. And was it open book or closed book? It was open notes, open book for this test. Okay. All right. So we're in section 10 point something. And so for a little while, we're going to be in 10.5 and 10.6. I'm sorry, that's incorrect. 10.3 and 10.4. And so I'm assuming now that you have had a chance to look at the parameterization of things that we did before we did the polar. So polar starts in 10.3. As I say, it's assuming now you can convert things. And I hope you've also done some polar graphs. So that if I say a cardioid or a lemniscate or a limescent, something like that, limicon in Kansas, some people, you know what to do. Okay. Yesterday we talked about tangents to polar curves, and the latter section was graphing with things, and that kind of ended that section, but I just kind of wanted to review it a little bit. What we want to talk about next is areas and lengths and stuff, to use the area idea and the length idea, which we developed for parametric representations. And the idea of area, when I have a polar graph, as we've drawn some, and the screen I have here doesn't show the thing I'm doing right now. So now I can see myself when I look back. We have a screen like this, and I hope it's good enough. The colored chalk went bye-bye today a little bit. And we have some beautiful things, by the way. They do a great job of washing the board, but they don't do a very good job of cleaning the, can you see this stuff? Anyway. So I don't use those erasers because if I do that, then nobody can see anything. So we've got a polar thing, and what you found when we've done these things, we've done something and we get stuff like this for polar graphs, okay? And they might do loops and whatever. So what do we base calculus on for polar graphs? And the answer is we base it on the sectors of a circle. Because what we want to do is take one of these polar graphs and partition. Now, partitions, as you know, as you're used to seeing some kind of a graph above something like this. And when we partition, we cut the thing up into a bunch of lines, and we make a rectangle. We decide to do that in various ways, as you know. And then we add up those rectangles. Those are area of the rectangle is base times height and stuff. And you guys know that's how we make Riemann sums. And then we make more and more partitions by making it finer and finer, by putting more points in the partition, making more rectangles. And we've been doing that and doing that and doing that. Okay. So what do we do with polar? Well, polar depends on the angle, which in radian measure is actually a number. And so we can think of an area as being different angles. We can think of an angle like theta 1 here, think of another angle like theta 2 here, for example. And but as numbers, it's like an interval. So what we want to do is partition up this interval. So what that's going to do is partition give us a whole bunch of sort of fan sort of thing. All right. And what you're going to have is a little difference of angle instead of a little difference of width here. Except these angles are in radian measures, so it is a little difference in width. It's the same idea here. But remember with polar, what we're doing is putting the polar coordinates on top of the rectangular coordinates. And so what we want to do is sum up a bunch of these areas of sectors and increase the number and so forth, and that's how we're going to get an integral. Okay, so that's the idea. It's on page 709, and he writes down equation 2. Well, equation 1 is the area of a sector. The area of a sector is a half. Now, this is a wrong formula, but you need to have a square someplace, and some people forget, but it's always going to be the radius that gets squared. This is the area of a sector of angle theta, and if it's on a circle, the radius is r. And we're going to use this to sum up a bunch of these, except in this case, we're going to assume a given r. The given thing we have here is like choosing the height over here in terms of height of the rectangle. And so that's going to be the r, and the theta will be the difference in the two little angles. So it's going to be like theta k minus theta k minus 1, really. It's the difference in angles that's going to make up the sum. And so you get the formula 2. And since the formula is, remember, r is f of theta, the f of theta takes the place of f of x here. Okay. And so anyway, you get an angle, an integral, and it's going to be 1/2. Okay, and we have to kind of generalize this idea here. It's going to be 1/2. And it says here in the book, f of theta squared. So where did the difference of the angles go? Well, again, to the inventors of all this stuff, remember there's a difference here. This becomes a delta theta, and delta thetas go to d theta. That's the way they thought about it. So the r squared becomes f of theta squared. The 1/2 is just there because that has to do with the area of a sector. And the delta theta, the difference in angles, becomes the d theta, again, in developing the formula. And the only problem is this is an indefinite interval. There's no endpoints here. We got to put endpoints. The endpoints are whatever the endpoints are here, and that means the first angle and the last angle. So this would be like theta 1 and theta 2 if one is the least and the other is the most. So this is the formula for the area of a polar. So what do we do in the book? We have examples, we have exercises. So, and they're kind of interesting. We've already done this a little bit, but you got to be a little bit careful for reasons we'll get to. Suppose I have r is the cosine of 2 theta. You should remember yesterday that when we did this, when we plotted it, we got something like this first, and we had a lot of symmetry going on. Anyway, we get some loops. How many of them, when this is even, you get twice as many. Now, something that I'm hoping that you discovered with one of these, the sine of the cosine, and you've got to find this out. With one of them, it doesn't look like you get twice as many. But that's because the second grouping of them, in this thing, when I do this, I go around and I will get, by the time I get done, I will get 4. What I just kind of got here right now is 3, just kind of doing this fast, all right? Sometimes what you'll get is the thing, but the whole thing is drawn like when you get to pi. And when you draw it, when you do more, it turns out it goes over the same region you were on before. So one thing is always going to show you 2 times. The other's not going to do that, but it really is 2 times. It's just the thing is graphed twice. So you can't see the second time. Okay, and the idea is, as I say, one of them does stuff like this, and the other one might do stuff like this. And in one case, when it goes over a second time, it'll go over this, or this one will make a different one. You've got to play around. I don't want to answer such things for you. I want you to think about it and try to figure out the patterns here for these things. Now, for this particular one, there are 4 petals. So if we want to find the area of this 4 petal thing, okay, and there's a nice picture in the book, but basically we have 1 petal here, we have another petal here, and so on. What do you think about the size of the area of the petals? They are equal. So all we have to do is find 1 petal and then multiply it by 4. Yes.
If we're thinking about area in terms of like positive and negative, wouldn't that be 0? Because there's equal amounts of negative area.
No, we're not doing it rectangularly.
Oh, okay.
What we're doing is summing up a bunch of these things. And so the height, the way, I'll get in the way here so people can see. When you're talking about rectangular, when the F is negative, that's when it subtracts. In this case, it's the angle that changes. The angle may be negative, but the F is still positive. But it can subtract sometimes. If some of the regions have the R going the other way, then you might get a negative. But in this particular case, we're squaring. And so even if this turned out to be negative, you square it. But I said a little while ago, we have to be careful a little bit. We don't want to do this all for all of these, because some of them might subtract from others, like you're thinking about. Like what you're thinking about is something like this, where the area here and the area here might be equal. When you add up the 2, you get 0. That can happen with these things. So what you want to do is get the area of 1 of them. And then we know it's 4 of them or 3 of them or whatever. Okay, that's one of the things we have to worry about. So what we want to do to find the area of cosine 2 theta is figure out what happens in 1 pass. And if you think about it, I think you'll realize that at pi over 4, we have the cosine is 0, and at minus pi over 4, the cosine is 0. So the angle involved here with the area of 1 petal is between minus pi over 4 and pi over 4. That will draw 1 petal. And then with the rest of it is fairly simple in terms of what we do, not how we calculate. We have to take f of x, in this case f of theta, and square it. And so we need to do cosine squared of 2 theta. Okay. Now, this is a problem in the book. And how do you do this? How do you integrate the cosine squared? You guys have to do it. Integral test? Already done an integral test?
Change it to its identity.
You could do it by parts, or you can do a half angle formula. Right? Now, we're not trying to learn how to integrate now. It's assumed you could do this if you want to take the time to do it. The new thing here is to say, what are we trying to do? In this case, is to use this formula. So the book does work it out. I don't care about that right now. I don't care about the answer. I just care about the setup. The next one's more interesting. The next one says, the next example, and this is a good one. This is the kind of stuff you put on tests. Okay. The next example is to talk about the area between 2 things. And one is a circle of radius 3, And I'm not gonna be able to draw this like the book does, but basically you have a relatively, something that's supposed to look like a circle, okay? The degree of that has to do with how much time you want to spend drawing it, except he says the circle is r equals 3 sine theta. So unfortunately, what I have to do is figure out how to graph this. And that's not going to be this one. In other words, we got to construct it. Now, supposedly you've been doing that. What you're going to find out, and we can plot a few points here, but the cosine of 2 theta, that was not a circle. 2 cosine theta, remember, was a circle. It was a circle that had a point on the circle, not the center, was where it went through. When you do this one, you're going to find out that it's like this. How do you know that? When theta is 0, you're at 0. When theta is pi over 2, you will be at 3. And so, anyway, you can figure that out. One other way to do this is to say, okay, r squared is 3r sine theta. And so x squared plus y squared, remember we can do that for circles. X squared plus y squared is 3y. And you can figure out this is x squared plus y minus something squared equals something is a circle. And the 0 and where this is going to be the center. And so on. You can figure that out. It's actually going to be half. It's going to be y minus a half. And over here it's going to be 1. Never mind, I don't care. But anyway, you get this circle of radius 3. Radius 3 halves. The other thing that you want to do, play with this, is it says inside the circle and outside the cardioid. So the other one is 1 plus the sine of theta. And again, if you've been playing with these things, that's a cardioid, that's got this loop, and what it's going to look like, and I may not draw a very good one, it's going to look like this. And so what we want to do is find this area right here. How do we do it? We need to find this point and this point because you're thinking of sweeping out a region. So if I find the area inside the cardioid from here to here, and I find the area inside the circle from here to here, in other words, I want to leave out this and I want to leave out this. So I want to subtract the area inside here from the area inside there. I've got to find out what these thetas are to do that. Now, that's one of the places where it can be difficult because r equals 1 plus sine theta and r equals 3 sine theta. What I need to do is find out where they intersect. If I set them equal, which I would be probably think I should do, then I get 1 plus sine theta is 3 sine theta. I get 1 equals 2 sine theta. I get sine theta is a half. And that tells me that theta is pi over 6. Maybe. What else might it be? Might also be something in the second quadrant. I'm looking for 2 points. So it might be pi over 6 off. So it might be 5 pi over 6. And so that's what I'm going to do. I'm going to find an integral from pi over 6 to 5 pi over 6 of something. And I'm going to subtract. So I'm going to have the circle minus the part of the cardioid. So again, this is the setup. You can read about it on page 710. Okay. As far as the computations go, that's not bad. Now, he says caution. Okay, and so we want to look at the caution. The problem is that, and we're going to do another problem here. So now we're going to look at this cosine again, I think, the cosine of 2 theta and the circle r equals a half. So if I look at the cosine of 2 theta, now that's going to be, again, this kind of a loopy thing. And if I have r equals a half, I'm going to get a circle. This time I'm taking this r equals a half as a circle with center at the origin. So what I'm going to get here is 4 loops, and I'm doing this fast because I get something like this. And what I want to find out is where do these intersect? Well, if you look at the picture, even if I just drew it awful on purpose, even if I draw it awful, I see that I got 1, 2, 3, 4, 5, 6, 7, 8 places where they cross. Okay, how do I find them? Well, what I just did is equate it. So equate. So what I have, this was r equals cosine 2 theta, I guess, and r equals 1/2. Oh, that's pretty simple. Cosine of 2 theta is a half. Well, the cosine of an angle is a half. That says if this was alpha, if the cosine of alpha were a half, that says alpha is pi over 3 or minus pi over 3, if you like, or you can think of this as 3 pi over 2. Well, minus pi over 3, you can think of going all the way around. It's 2 pi minus pi over 3 if you want to do a positive one. And so that would be 5 pi over 3. So either one of these ideas, a negative or a positive, and this would give me the 2 answers for alpha in the circle. Now, that's not, I don't have alpha, I have 2 theta. So theta is going to be pi over 6, pi over 6, or 5 pi over 6. So I'm making this a little heavier. These are 2 answers to my problem. Okay. Now, what's wrong with that? I'm looking for 8 answers. I just found 2. How do I find the other 6? Well, maybe I forgot something. Because the book in example 3, they find 4 points. I just found 2. What he says, 2 theta is pi over 3, 5 pi over 3, 7 pi over 3, or 11 pi over 3. Okay, I'm kind of dumb. Why does he find more? Because he's talking about doubling here, right? So the angle can be less than 2 pi, and twice it would be more than 2 pi. So I've got to find more angles, you understand? If I would take 2 pi plus pi over 3, that also would have cosine a half. That is 7 pi over 3. So if I had the cosine of 7 pi over 3, that would also be a half. But I don't have that, I have twice that. So 7 pi over 6 is going to be an answer. And in other words, there's 2 answers more than 2 pi. When I take half of the angle, I get less than 2 pi. That's going to give me, well, I got to look and see here. We're going to get this one, and we're going to get this one. And then I'm going to get this one and this one, I think, by realizing that half of something more than 360 is less than 360. So I wasn't so smart. I only got 2 to start with. And then somebody tells me there's 8. Shoot, I'm not very smart. Well, then I figure out, oh, I can get 2 more by going around a little further and taking half of that. Now I got 4. But you can see there's 8. In other words, solving these 2 equations simultaneously does not produce all the answers. So how do I find the other 4? Look in the book. No, you can do that, but okay. If you think about it, and thinking is the whole idea with this stuff, because it's new to you. You ought to be looking at it and thinking, how do I do this, and what do I do, and how do I do more? The thing that came up a minute ago about minus area, what about R being negative? Remember when we draw some of these things, sometimes the R is negative because the cosine is sometimes negative. So if I solve this with a minus, if I put these 2 things together with a minus instead, then I'll come up with the other 4. Because it turns out that 4 of these happen when the angle is minus instead of plus. But the idea of it, the reason he says caution and so on, is to point out that just solving the equation like I did here, this gave me both of them here. So if I do this, even if I'm more clever than I was to start with, it only gives me half. So there's an infinite number of angles that give me the same sine and cosine. So you have to be careful. There's more than one answer to these things. Okay. Now, the section 711, page 711, has at the bottom arc length. So there's one more formula we got to learn. Okay. So I don't want to go all the way through that, but we'll go through a part of it. To find arc length, if I had a parametric representation, remember, hopefully you remember because we're going to have a test over it. I have a parametric representation where I have a parameter from alpha to beta, drawing my curve, and I have a Vt on there. This is the formula for length of the curve. Well, I have polar now, but what I'm going to do is construct an x of theta and a y of theta. And the way we did that yesterday, because what we have now is r equals f of theta. So what we're going to do is say this is f of theta cosine theta, and this is f of theta sine theta, and stick these 2 things into this formula. That's how you do it. Now, it's a little bit messy because the formula says the derivatives, and also t is theta. I think that's easy to understand. So t in this case is theta. I need to find x prime, I need to find y prime and square them and add them. Yeah, I don't want to do that because when I find x prime, okay, I'll find x prime. X prime, what do I do? Oh, I don't like this. It's a product rule. We get too many things because it's f prime of theta cosine theta minus f of theta sine theta. That wasn't so bad, but what I've got to do to the thing, I've got to square it. I don't want to square that thing, but you got to. Or read the book. Book does it. Book does it for me. Hey, there it is. Okay, I see it. Yeah, it's right there. Anyway, the idea is you have to square this and square that. What, by the way, is y prime? Just because I want to prove I'm not a slouch here. Y prime is going to be f prime of theta sine theta plus f of theta cosine theta, right? Okay, now let's just think about it a little bit. When I square both of these, don't want to do it, but when I square them out, what am I going to get? I'm going to get the square of this thing minus twice the product of a bunch of stuff, right? Plus the square of the last thing. What am I going to get down here is the square of this thing. So what I'm gonna get is f of theta squared cosine theta squared plus f of theta squared sine theta squared. That's part of my answer. So they will both have f of theta squared and cosine squared plus sine squared by factor, that's 1. So when I square this thing out, I'm gonna get 3 things. If I look at the first ones here, when I add them up, I'm gonna get f prime of theta quantity squared times 1. I'm gonna have minus twice all this junk, and here I'm gonna have twice plus twice all this junk. When I add those two together, it's gonna be 0. Okay? And what's the last one gonna be? It's gonna be this thing squared, and this thing squared, plus this thing squared, plus this thing squared. Here I got sine squared plus cosine squared again. That's gonna be 1. So shoot, this isn't so bad. It's more like f of theta squared, something like that. That's kind of like what it looks like, square root maybe. You guys got to do this carefully. But did I do it right? I don't know. I've never looked at this page before. The book says it's r squared plus dr d theta squared. So the book loves to do dr d theta. They don't like primes. This is what the book says the answer is. Is that what we just got? If r is f of theta, what's dr d theta? That's f prime of theta, right? So if instead of this one, I write f prime of theta quantity squared, and instead of f of theta is r, I write r squared. I did it. This is how I would rather you look at the answer. To use the formula instead of the r. See, when you do this, you've got to change the r to the f of theta because you're integrating with respect to theta. So why not have a notation that tells you? So when I learned this one, not that one. Well, that's not true. In high school, I learned that one, but I never understood it. Later, when I'm looking at it, I learned this one. So that's the other thing that's in the section. That section's over, it's done. And we have next conic sections. Okay, plus a pot full of Weber-Sign problems. And as you guys know, we cut down the Weber-Sign problems. Just do a few. Don't worry about getting 5,000 points. But do something. I will give you a couple of points if you're a good person and you've done something. Anyway, the next section's conic sections. And we don't have time to do it much today, but I have time to do something today. And so I want to sort of talk about something that's been around since the Greeks' time, 2,000 years and so on. It's in China and probably Japan and various other places where people dealt with stuff like this. We want to look at the following thing. This won't have anything to do with what we do shortly, but for a long time, people wanted to know something about a formula, an equation like this. In other words, if I have a quadratic equation in one variable, we know about such things. You have two roots and so on, and we study them. If you set y equal to x squared, most of you know you get a U-shaped thing, and we call that a parabola, and so on. And so you all have some stuff involving this. Well, somebody might want to study the set of all x, y, such that this equation is true, okay? What kind of graph do you get if you choose A, B, C, D, E, and F? What kind of graph do you get? So for example, suppose I choose 2x squared plus 2y squared minus 1 equals 0. What kind of a thing is that? I think you should recognize that as a circle. So if I choose A to be 2, B to be 0, C to be 2, D to be 0, E to be 0, and F to be minus 1, you get a circle. Okay. Suppose I choose A, B, and C to be 0. then I'd have dx plus ey plus f. I get a straight line. Okay. So do you see that it might have been attractive to some math person a couple of thousand years ago to play around with choosing different values here to see what kind of graph they get by plotting points, if nothing else? This equation includes straight lines, and not just non-vertical straight lines. Why do we deal with non-vertical straight lines? Because we want to talk about derivatives and slopes. But if I would let a lot of these things be zero and just say that all of them be zero except for this, I would get ey is minus f, and that's is that a horizontal line or a vertical line? If y equals a constant, is that horizontal or vertical? Y equals, that's horizontal. Okay. But if I let e be zero and abc and did dx plus f, I get a vertical line. So this setup includes all lines. Okay. And it includes all circles. So, as I said, a couple of thousand years ago, people studied these things. And by letting different things happen, for example, if I would make this minus, it turns out when you graph these things, you get certain pictures. Now, let me give you another one that's very simple. Suppose that A is 0, C is 0, D is 0, E is 0, and F is minus 1. And B is 1. Then I get XY is 1. What's this graph look like? I don't know. But if X is not 0, can X be 0? If X is 0, I get 0 equals 1, which is not good. So X can't be 0. If X is not 0, I can divide by it. I get Y as 1 over X, and you all know you get this picture. So if B is not 0 here, I get this kind of a shape if it's all simple. Now, if you forget where horizontal is and think horizontal is this way, and you look at this, then for other people who think horizontal is this way, okay, they would get this picture. Understand? So if you turn your head and say, take that paper and then make it normally horizontal, this is what you get. Right? Well, it turns out that this has a name. It's called a hyperbola. But the way people study these things is, it turns out, based on lines and points. And people study these things with a vertical line or a horizontal line. In other words, they decide, when I just said a vertical line or horizontal line, I already decided what vertical, when I say that, it's like you already get a picture in your mind. In other words, if I said that's vertical, people would think there's something wrong with me. Now, you know there's something wrong with me, so you probably accept it. Like he wants to say that's horizontal, well, he's going to grade me. What am I going to do? Complain? No. So you go along with me. Anyway, what I'm trying to get at is, we're going to find out that there are certain things that look like this, or they look like this. And there's going to be something like this that's either horizontal or vertical that they're on either side of. Some of the things that solve this problem look like this or look like this. Okay, and so it turns out we're going to get equations involving things that look like this or things that look like this. And then it's going to turn out that something like this is going to be a rotation of something like this. If I would take this and rotate it, you get a picture like this. Okay, so it occurred to people after a while if this is 0, if B is 0, so if this term is not there, if it's gone, then everything else you've already studied a lot of, meaning if I now look at ax squared plus cy squared plus dx, and now I'm going to change things a little bit. I'm going to say, oh, I don't want to do that. I want to do dx, and I want to put cy squared plus ey, and I'm going to put f on the other side. You see, now we've had some training, I think, in our previous worlds. To study something like this, we can complete the square with stuff like this. We can complete the square with stuff like this. Maybe. You understand? Now, completing the square, you got to divide by a first. So the a has to not be 0. So that's a case. Suppose a is not 0. Then we can divide by it and get rid of it, basically, because once I divide by it, I have x squared, I have d over a, but that's just another number. I haven't told you what d is. So basically, once I say a is not 0, in that case, I can make new letters and simplify things a little bit. And you can start studying different things you get by making different assumptions on what a and so are. And it turns out that all of these turn out to have things involved with them that are either vertical lines or horizontal lines. I don't mean the things themselves are, but they're related. For example, we may have something like this and this line. This might be a parabola. Okay, if there's a thing up here, it might be what's called a hyperbola. Anyway, when you don't have a B, it turns out that there are vertical and horizontal lines that are involved with studying these equations. These lines are called, one of them is called a directrix, D-I-R-E-C-T-R-I-X, a directrix. And that's a Greek third declension word. The plural of directrix is directrices. Instead of the X, you replace it with CES. That's what you do with all the things like vertex, vertices, vortex, vortices. Maybe you know that, maybe not. When you plural something with it ends in X, you make ICES. That comes from the Greek language in English, because English is a compilation of several languages, as you probably know. Okay, so anyway, when the B is 0, it's going to turn out there are directrices that are vertical or whatever, whereas when the B is not 0, it's going to turn out that if we've studied all of these, we can study all the ones with B not 0 by twisting the thing. And so the equation of these things, the equations are called conics. Conic, and the other word is section. Now, section is a word that means cut. Bisect means cut into 2 pieces. All right. If I have a section of land, I have a cut of the land. I mean, it's part of it's mine and it's cut off from other parts, a section. So section we use in mathematics, but these are called conics, and they're also called conic sections, but that gets into more than 2 dimensions. Right now I'm talking in 2 dimensions. And if the B is not 0, the conic is called twisted. So when I have an equation and study conics, if the B is different from 0, I have a twisted conic. And the point is, we can study all twisted conics as rotations of non-twisted conics. So one way of studying conics is to study conics with vertical and horizontal directrices. And after we get that study completed and know all about it, then we can take all the pictures and rotate them. And we'll get the same shapes, but rotated. This one is rotated 45 degrees. This equation right here is a conic that's rotated 45 degrees. So we don't need to study this. So what people do is they don't study this at first. They study it later after they studied all those others. So one big case is to let B be zero. So you have case B is zero, another case B is not zero, see? Turns out there's like 15 cases here that you have to worry about. This is one way to study conics. Okay? It's 19 after. What's another way to study conics? Take a cone. Now, we've talked about this before. If you go to an ice cream store and order a cone, you get something like this, hopefully with something in it. Okay? Because see that, actually, you know, when you say I like the ice cream cone, they just ought to give you one of those. No ice cream in it. Right? As soon as you put ice cream in it, it's no longer a cone. I said, sorry to tell you that. Okay. But actually, a cone has two halves. And so when I go to ice cream store, I always ask them for the other half. And they never understand what I mean. And if you explain to them it's a double like this, if they give this to you, you really got to eat it fast. You got to really, sort of like somebody leading the band, you know, with a baton, because you got to learn how to really go fast. I'm going to turn off the recording now because we're over time. But I don't want to add a question. No, thank you. Hit the wrong button.